So first of all, thanks for the invitation. It's my first time at coming to JHU, and I must say that also congratulations to you on the opening this institute. I think it's a great way to bring people together, particularly applied people and the more people working on more mathematics of data science. I guess Joel emphasized the importance of this fusion, and my talk will bring up some more of it. In fact, it's the main challenge for the kind of things I'll talk about, how to get the domain experts to talk to the theory people, because this is an area we really need, particularly of interactive algorithms, where we need to bring these two together. Okay, so I'll talk about interactive algorithms. Before I tell you what I mean by that, let me start by saying what classical approaches are. So the standard approach to data analysis is that we have a data that one of our collaborators has or a domain expert has, and they give it to you and ask you to do some analysis. So it's sort of a one-way street in the sense that the data is presented to the algorithm crunches the data and outputs some knowledge, right? And of course, the algorithms are getting more and more intelligent in terms of how they can process this data. But the specific setting I want to talk about is interactive learning from data. So the idea is that the algorithms not only process the data, but they're also involved in how the data is collected. And is there feedback that can be used potentially from looking at some data that can guide the collection of new data points? Okay, so that's what I mean by interactive, and it'll become more clear as I describe specific setups and specific projects in which this comes up. So, but the idea is that the algorithms are sort of becoming more intelligent in that not only they're processing the data, but they're involved in the data collection aspects itself. So first of all, yeah, why can we do that? There are increasing number of applications where we actually have control over how the data is collected. And right now, the decisions about which data to collect are sort of made in an ad hoc manner. There's a person who just decides to try out certain settings. Maybe in the case of vision, there are images that are chosen in some ad hoc manner to decide which ones to get labels for, because there's clearly a constraint on how many images can be labeled. We can't hope to label all possible images in this world. So somebody is choosing these data sets and asking for labels. Similarly, applications that I work on, so these are two collaborations I have with neuroscientists and some material scientists, where they're interested in understanding, well, in the case of neuroscience, the brain. And anybody who's been in an MRI scanner knows it's not a pleasant experience. At least you can't be there for very long. So they are limited in how many stimuli they can present to you while you are in a scanner. And again, the question becomes which stimuli to present, right? And they have control over, so if you are trying to understand the human visual system, then they have control over which images they'll show you while you're in the scanner. And can we choose these images in real time based on feedback to tell you the most about what's going on in the brain? Okay, so that's an interesting again, application where we clearly have control over what stimuli to present, and it's important to optimize what stimulus we show. In the material science case, we are again looking at my collaborators trying to achieve a particular type of material, and the question is, what are the experimental settings, temperature, pressure, ramp time? They have a lot of different things that they can control that they should try to perform this experiment in to try to get the material. And of course, there's clearly a need here for trying to control, because they're working on a limited budget, on how many experiments are done, right? And you can think of any other application, like which drug and gene interactions to record, which questions to ask in a crowdsourced setting, or which routes to measure if you're taking measurements on a computer network, let's say, right? So in all of these cases, we have control over what data should be collected. And moreover, well, of course, people say nowadays we have so much data, so why should we worry about which data to collect? There's big data, but I think my response is there are bigger systems, right? We are trying to ask more and more questions. We are trying to understand our systems in more detail, in more complexity than ever before. And the systems themselves are getting much more complex that we can't hope to measure them everywhere and all the time. Right, so there's clearly an opportunity in terms of us having control over which measurements to take, but also a need, because we cannot hope to measure them all the time. And we need to design intelligent algorithms that can generalize using the most informative data. So they can be involved in the process of which data should we choose. Right? So with that, let me present two specific aspects of intelligent interactive algorithms that I'll focus on. One of them is experimental design, which actually has been around for a long time in classical statistics. But I'll mention some of the challenges that come up. In particular, the mathematical challenge that comes up is a combinatorial one. So what is experimental design? You can think of it as one round between the algorithm and the data. So a practitioner presents the set of possibilities it could collect, and the algorithm looks at it and decides, tells it, this is the subset that you can maybe get labels for and give it to me. It's just a one-way interaction. Okay? The data is presented, or the domain is presented of all feasible data points, and the algorithm tells it, under a budget of, say, k points that you can get labels for, here are the k ones that you should present to me. Okay? So this is a combinatorial problem because typically you have a larger pool from which you have to choose, and you have to choose under a budget on how many data points can be measured. So say k out of n if you have n data points, and if you were just searching for it brute force, then you would have n choose k possibilities, right? So that's clearly combinatorial. So the mathematical challenge here comes up when we are trying to scale this up to lots of images and lots of data points. Then how can we do that? The second is active learning, which is a sequential version of this, where a data point is presented, the algorithm decides whether it needs to query the label or not, and then based on what it learns from that label, it decides which is the next data point to collect a label for. So it's done in a sequential manner, and the key challenge here, as you can see, is that our data points are no longer independent, right? Their data is not IID collected. There are, every new data point which is labeled has a dependence on the previous one, because it was chosen based on the value of the previous data point. So mathematically, that's the key challenge that comes up. Now we have to control this, our inference and prediction procedures by taking into account this dependence between the data points. Okay? So I'm going to, I'll get into a little bit more mathematics and details of some specific problems in a minute, but I wanted to give you a high-level idea of what's sort of rule of thumb that has emerged from at least the amount of work I've done in this direction. So, and it's actually pretty intuitive once you hear what it is that when does experimental design help? So if there is any kind of heterogeneity in your problem, okay, heterogeneity meaning not all labels are equally, expensive or equally important, right? In those cases, clearly, that's when you would need interactive algorithms, right, that can choose the right subset. So if that heterogeneity is known, then experimental design can actually adapt the data collection to focus on the most informative part. Okay? And if that heterogeneity is unknown, and I'll give some examples of that, but there is heterogeneity in your data, but you don't know the exact form of it, that's when sequential experimental design, or what's also known as active learning, helps. Because in this case, you first need to take some data and learn about the heterogeneity, and then adapt the data collection based on that. Okay, so that's a high-level theme I'll try to come back and touch on, that if, first of all, there has to be heterogeneity. If all your data points are homogeneous or equally important, then clearly interaction does not help. And even when there's heterogeneity, then depending on whether it's known or unknown, that guides whether you should be just doing a one-shot or experimental design or a sequential procedure to optimize the data. All right. So again, to drive home this aspect a little bit, let me give you an example. Again, without going into too much math, this is at a high level, that of denoising graph signals. So suppose I have, let's say this is a road network, and the different locations are the intersections where I can equip them with a sensor. But I have a budget on how many sensors can be placed, maybe to measure pollution levels or something like that. And so the goal is, under a limit on how many nodes can be measured, and assuming a simple model, signal plus noise model, we want to reconstruct or denoise what the graph signal is at all the nodes. Okay? So in this case, the reason I'm choosing this particular example is the graph structure, the road network, is known to us. The signal is unknown. Okay, and I just want to, again, drive back the point about known heterogeneity and unknown heterogeneity, and when experimental design or active learning helps. So the graph structure is known. Of course, the signal is unknown because it's corrupted by noise. And so we can look at different cases. If my graph is regular, say it's a grid graph, a very regular graph with uniform degrees, and my signal is smooth, meaning it's nice and changes gradually over this graph. In that case, there's nothing special about the graph. Every node is equally important in some sense, right? And so because my signal is smooth, again, no particular signal is more important than any other. It's homogeneous smooth. Okay, in that case, we can actually show that passive learning, which is the classical learning, doesn't do anything intelligent, or randomly subsamples, let's say the nodes here, is same as experimental design, is same as active learning. Okay? If I have an irregular graph, but still a smooth signal, a signal that behaves nicely on this graph, then you can show that experimental design can leverage the fact that we know the graph, which is heterogeneous, but we know it, and actually improve on the passive results. But active learning does not buy you much more because the heterogeneity is known. Your graph structure is known. Signal is still smooth. All right? And the third setting is the case where my signal is heterogeneous. For example, it's not smooth. Maybe it's localized on the graph, or it's a binary signal. So some of the values are, let's say, 1, others are 0, as a simple example. In this case, we have the signal, which is unknown, and my graph could be regular or not regular. But because there's unknown heterogeneity, now active learning can actually outperform experimental design, which can outperform passive if the graph is irregular. Okay? So I don't know if it helps, but hopefully at a high level it conveys the idea of experimental design versus active learning and whether heterogeneity, known or unknown, helps. Okay? So with that, I'll try to go a little bit more deeply into some of the problems and come back and make connections to this idea. So the first thing I'll choose to focus on, so I'll give one example of experimental design. Hopefully there's time. One example of active learning where we have made some contributions and talk about interactive algorithms in these two cases. So the first is actually a very simple model. So I wanted to, if you still want to think of the graph setting, then the simplest way is we are assuming a linear regression model for a smooth graph signal, by which we mean that my signal can be represented as x times beta, where x are some graph features. For example, these are, sorry, this thing will keep popping up, the wireless, I should have disabled it. Okay, hopefully not. So yeah, if my signal is smooth, then I can write it as x being, for example, the first p Laplacian eigenbasis of this graph. If you don't know that, think of those as just some road features, okay, and or based on the graph. And beta is my regression coefficients that I'm interested in recovering, or basically doing a prediction, which means recovering S for all the nodes under a budget on how many of these can be measured. But I'm going to go away from the graph setting and focus on the simpler setting of just linear regression. Let's say I just have a linear regression model. Y, my observations, are x times beta plus noise. So we can forget about the graph now. Any x, it's a design matrix that's given to you. Your measurements are a linear combination of them, corrupted by the best possible noise, which is IID, Gaussian, zero mean identity covariance. Okay? And the question is, we actually don't have access to all of these y's. We have a budget on how many y's can be measured. All right? So what if I can only collect k labels? You can think of the y as labels. And there are n possible labels. But I'm telling you, you can only collect k of those. Then which ones should we collect to learn this regression model the best? Okay, so it's a very simple, now mathematically concrete question I've posed. We'll focus on the large sample setting for simplicity, which is we have, this is a tall matrix, the design matrix. I have many more candidate settings for which I can try to get the labels than the number of features. All right. So we can ask two questions. One is that of estimation, which is we want to recover the regression coefficient vector beta, and another is that of prediction. That is, I want to predict the label, which is just z times beta for some data z, which could be different from x. Okay? So of course, we know what the, if we had access to all the labels, it's the classical OLS solution, ordinary least squares, right, which just minimizes this least squares norm. And the solution is given like this. It's a simple exercise to work it out. And we'll be focused on, depending on the question at hand, either estimation or prediction. We'll be looking at the estimation error or the prediction error, which for this specific estimator, the OLS estimator, can be written like this. Okay, again, a simple exercise to work it out. So of course, I mean, this is a very classical problem, and in statistics and experimental design, people have been looking at it for a long time. What if I don't have all the y's? This is the solution when I have all the y's. If I can only measure k of those, here's a solution that comes up in experimental design and classical statistics, which is I just look at this objective, right, which is the error estimation or prediction error of my OLS estimator, and I just compute it over subset. So instead of the full x, I compute it over subset of k rows of x, all right? And I just pick the best k row, set of k rows. So I have S, which is a subset of rows I've chosen, for which I'll collect the labels. And I'm just saying minimize this error, right, over all subsets of size k. What's the issue? I mean, it has been around since like, I think at least the early 50s or 60s, why not even earlier, is that it's combinatorial, right? So again, we are talking about n choose k possibilities, so it scales badly if we have a lot of data points. So before going on to our proposed solution, so that is where I was saying, like in experimental design, the main question comes up is sort of this selection, combinatorial explosion. But let me mention another line of work which is very related, actually I guess related to some of the stuff that Joel had mentioned, which is that of speeding up computing the full sample OLS solution. So first I want to pause here and say the goal is slightly different. We care about, we have a budget of k measurements that we can make. Here you do have access to all the measurements, but the goal is just to compute that full sample solution faster. But the reason I'll mention some related work here is because some of that work is based on sampling. It just says I'll sample some of the rows of this matrix, and they tell you how far then, if you solve using the subset, how far is the solution from the full sample OLS solution. And you can think of that, well, I can use the same algorithm to do measurement constraint setting as well. So perhaps the most related work is by Avran and Baptistis in 2013, who proposed a set of greedy approximation algorithms. And they were focusing on this looks like slightly different objective, which is the Frobenius norm squared of the pseudo inverse of a subset. But if you just rewrite it, it's the same objective as ours, which is the trace of XS transpose XS inverse. And they show that they give you ways in which you can choose this S in polynomial time, such that this objective is within, I read this as being n by k approximation factor of my full OLS solution, all right? The issue is that this is actually same as uniform sampling. You can find worst case matrices for which this will hold true, right? So while it's nice because it gives you a guarantee for how well you can approximate the full sample OLS, I want to ask the question, can we improve this approximation factor if we care about not the full sample? Let me, sorry, turn this off if I can figure it out quickly. Oh, yeah, maybe that's easier. Yep. Okay. All right, so I want to ask the question, can I improve this approximation factor to 1 plus epsilon if what I care about is not approximating the full sample solution, but I want it with respect to the best k subset that can be chosen? Okay. So I want to replace this with the best k subset that can be chosen, which is given by these classical statistical optimality criteria, and I want a 1 plus epsilon approximation here. So yeah, that's just my question. And actually it turns out there is, recently people did look at this problem of can we use all the techniques we have for sampling matrices or computing the OLS solution faster and see if we can get something better. And in particular, some of you may have heard of this Leverett score sampling, which is related to effective resistances in graphs. And this is a common sampling technique for matrices that people in theoretical computer science community have been looking at for a long time. And in a series of papers, which basically combined Mike Mahoney, being one of the CS theory person, with Ben Yu, who's a statistician, saying, what if I have this linear stochastic model, and I actually cared about recovering its parameters, not some worst case model, then how well does Leverett score does? And it turns out they actually show while Leverett score is again very good at approximating the full sample solution, it can be worse than uniform sampling for doing this measurement constraint setting. Okay? But I will compare, the reason I mentioned these two is we'll actually use the greedy, except we won't apply it on the full sample. We'll apply it on some subset we have chosen to get better results. And I'll also compare against Leverett score. So I just thought I'll mention these. All right, so what do? We take our, So again, going back to the holy grail, which is these are brute force solutions. These are the best possible you can aim for. You search for all possible subsets. I'm going to take these objectives and think of this as here in between I have a matrix, right? So I can write it as X transpose times a binary matrix times X, where I have on the diagonals ones or zeros depending on if that particular row was chosen or not. And I'm just going to relax it. Instead of requiring that diagonal entry to be 0 or 1, I'm going to allow it to be between 0 and 1. So it's a convex relaxation, a simple idea. So we come up with these objectives, which are the same as before, except now I am putting in a diagonal matrix here whose entries are pi, and they lie between, well, actually pi over k can be thought of as a probability distribution. Okay, so essentially pi, if I look at pi over k, this is saying that they sum to 1, pi I is over k. So pi over k can be thought of as, I'm now flipping a coin with probability pi, to pick the row instead of just saying pick it or not pick it, right? And the upper bound constraint of less than equal to 1, or if I divide by k, 1 by k, is simply used if you care about the without replacement setting. Okay, so you can, if you don't want to bother with the details, you can sort of forget about that upper bound. But essentially think of pi over k as a probability distribution with which we will sample the rows or columns. Okay. Just a quick note that these are now convex programs. They can be solved using semi-definite programming, which is nice that these are not combinatorial, they are convex, but SDPs are not too good. Actually, it turns out they can only scale up to problems of size 200 or 300. So what we do in practice is actually use projected gradient descent, and we can show that each iteration in the projected gradient descent for these objectives is actually linear in n, which is nice. And moreover, we also have a bound on the number of iterations. I'm just not presenting it. I think it can be improved. So if anybody here is an optimization guru, I'll be happy to talk to you later on. Okay, but let me focus on the more statistical aspects. What about the approximation we can get? So before we get to that, let me say we solve these programs. The solution is, let's call it pi star. It's a sampling probability. But now I need to take this pi star and convert it into a subset. And there are many ways you can do that, depending on how you use pi star. You could just sample according to pi star, but I'll also mention other ways and compare the results. All right? And what our goal is then to show that these convex solutions, of course, they lower bound the combinatorial objective because these are relaxations. But we also want to show that this objective upper bounds or provides a 1 plus epsilon factor approximation to the estimation or prediction errors. Okay? So that's the goal. All right, so let me show you a table of results for different ways of taking this pi star, which is the solution of this convex program, and converting it into a subset. So here's the first result. If I just sample with replacement according to pi star, the rows of my matrix, and say this is the subset I'm going to then do an OLS on, collect the labels for it, I'll do OLS on it. Then we can show that you get a 1 plus epsilon approximation, provided you are choosing order k rows, where k scales like p over epsilon square, p being my number of variables, and epsilon being the guarantee I want, right, 1 plus epsilon. If I want a hard constraint, if I want to say I should not choose more, if k is my budget, I should not exceed it at all, I want to pick exactly k rows, not order k rows, then it turns out your guarantees are a little bit worse. You need k to be order p, but you only get a order 1 approximation. Still better than the n by k, but it's not 1 plus epsilon, right? So the question is, can we get a relative error approximation with hard budget? Because in many applications, you do have to respect the budget exactly. Okay, you can't say 10 times k is okay. Before I show you some improvements on that result, let me tell you the key proof idea. It's literally 2 lines and actually goes back to what some of the work that Joel was referring to. So the idea is we choose some subset S, right, according to these sampling probabilities. And then we just obtain our beta hat, the regression coefficients, by doing OLS on this subset. Right? So I choose the subset, I collect the corresponding labels YS for it, and I'll do OLS on it. I look at its mean square error. That's just, we already saw the formula earlier for a subset S. It's given by sigma square trace XS transpose X inverse. And the only step I need to show is that this is less than 1 plus epsilon times sigma square times the trace of this matrix, which is basically my objective, my convex objective. right? So all I need to show is this one step. And notice that the trace of the matrix is the sum of the inverse of the eigenvalues, right? So as long as I can show that the eigenvalues of this matrix are close to the eigenvalues of this matrix within 1 plus epsilon, you have your result, thanks to Joel, right? So we actually did that. We also went back and looked at actually the work by Spielman and Srivastava, and actually some improvements over that since then. But this is the result which basically tells you on how to relate the covariance matrix of a subsampled set of points to another matrix, which is basically, in our case, this particular matrix coming in our convex optimization problem. And we can essentially use all these results on graph sparsification. They come up in the context of sparsifying graphs, but graph matrices are the same thing, right? So you can apply it here. And we use it here to talk about how you can get this 1 plus epsilon approximation. Having said that, let me point out a few things. So it turns out you can take any result on graph sparsification and it will imply an improvement for our problem. But there are some differences. Notice that we only need one-sided control. So typical results look like two-sided, right? So they are saying the eigenvalues of sigma star are sandwiched between upper and lower bounded by the eigenvalues of sigma s, the subsample matrix, right? Both ways. We don't need both ways. If we just want to give this guarantee, one way is enough. So what we are seeking for is sort of a one-sided but unweighted sparsifier, unweighted because I'm just picking the points, not giving them a weight, for a weighted graph where my weights are actually given by pi star. So if you want to relate it back to the graph sparsification problem, this is really all we want. And so under that set, maybe you can actually improve the results that we get. And the second point is, again, if you look at the trace of the inverse of this matrix, which is the sum of inverse eigenvalues, essentially all I care about is preserving the smallest eigenvalue. As long as I can make that smallest eigenvalue as large as possible, then we are good. That's all. I want to choose the subset which maximizes the smallest eigenvalue of the submatrix I've chosen. Okay. So again, we use this result, but we require something weaker. Right. And in fact, I'll show one of the improvements actually comes from realizing that we just want to maximize the minimum eigenvalue, and there are more direct ways to do it than use these graph sparsification results. Okay, so first, so let me mention one improvement. So this one we came up with by just saying, well, if you look at our convex optimization problems, they have this sort of L1 constraint on the pi stars, or something that looks like L1 constraint. So maybe my solution is already sparse. What if I just look at pi star, the sampling probability, and see how many of them are non-zero, and they are going to be few, and I just pick those rows. We did that analysis. It turns out we can only show it has p square. It picks p square and of the rows. Ideally, we would like to get p. So because you only need as many equations as unknowns, right? And there are p unknowns. So what we do is we actually do a greedy pruning of that support. So you apply the greedy procedure from Avron and Batistas on the support, and we can show that you actually get an improvement. You can get 1 plus epsilon with a hard budget constraint, where your budget k scales like p square over epsilon. Yes?
Just for clarification, so the p is the total number of variables.
P is the number of variables, yes. K is the ones you want to choose. So K is the budget.
And so how big are the constants? Because if it is on the order of P or P squared, then K is not small.
Oh, no. So any dependence on P or epsilon I've captured already. Is that what you meant? Or sorry, I missed the question.
So omega is of the order of? Or?
Yes, so there are some constant here.
Yes.
But they don't scale with P, right? I mean, they are constants. So it depends on the particular application, right, how big they are. And I'll show you actually, simulation and real data examples where it actually does.
No, what I'm asking is polynomial on P versus logarithmic on P. So
whether the constant is...
no, that I would have expected the K to be much smaller than P, but it's all the same.
No, K can't be much smaller than P, right? K is the number of equations you want to collect the labels for, so it has to be at least P. That's a bound we know. Right? We have to sample at least P, otherwise there's no hope. And if you only, and somehow epsilon also has to come in. Okay. So it's nice that this greedy pruning of our support actually gives us under a hard budget a 1 plus epsilon guarantee, but It's slightly worse requirement on the budget because here, remember, k was p over epsilon square. Now it's become p square over epsilon. Okay, so yeah, can we improve it more? Somehow our intuition, I mean, or okay, an ideal scenario would be if you could say, I only need to sample p over epsilon, right? Question is, can we get to that? We haven't completely closed the gap, but we can show that you can get at least under nearly like, I guess this one, yeah, nearly a hard budget, right? Or under a hard budget with p over epsilon square, we can get a 1 plus epsilon approximation. This is recent work that appeared in ICML, and this is actually based on this sort of, again, I don't have time to go into the details, but this idea of trying to maximizing the minimum eigenvalue of a matrix. You're trying to subsample a matrix such that you maximize the minimum eigenvalue. You can pose this problem as a regret minimization problem, and actually there were a couple of papers trying to do that. We just ported it to our setting, and using that particular algorithm, we can get these better results. Okay. So without, again, trying to go too much into it, so we haven't proved the dependence on p. Epsilon is still epsilon square, and it remains an open question whether we can get it down to choosing nearly k, hopefully exactly k rows, and that are only like p over epsilon, and still be able to get this 1 plus epsilon approximation to our combinatorial objective. Okay. So let me first mention some extensions, possible extensions, and then I'll show you some simulation results for this case. So one of them, of course, is, as I just said, this mathematical question that's open, but also the high dimensional setting. Everything we did so far focused on the low dimensional setting. And for high dimensional setting, there's no analysis, but people have proposed, well, maybe you use half your budget to first get an estimate of which are the non-zero coefficients, and then you just do your the same convex problem on the lower dimensional setting now. Whether that's optimal is unclear, but people are using it for things like, actually the same convex program I just proposed, but preceding it with using half the budget to get your regression coefficients for problems like fMRI, where you're trying to decide which frequencies to measure in fMRI. Again, if somebody is interested, I can tell you more about that. But it's not clear, again, what are the theoretical properties, what are the guarantees that come out of such a procedure. Another related thing that my collaborators come up with is sometimes you don't care about whether I can measure something or not measure something, but how accurately you can measure it. So you could have a bit budget constraint on, I have my labels. If my labels are coming from sensors, maybe I need to allocate different bits to different sensors on how accurately they measure something. And in that case, turns out even if you write out what we just did, it leads to a non-convex program. So it leads to a much more challenging problem that I'm again happy to discuss offline. Okay, so just some simulation results here. So this is for, again, comparing a bunch of methods. Generated data first generated according to the linear model exactly with this noise. Uniform sampling, leverage score sampling, predictor length sampling, which is basically same as this except for assuming sigma x is like identity or close to it. These are the two relaxations I talked about, doing the convex relaxation followed by sampling or followed by the greedy pruning procedure. And Fedorow's exchange, I don't have time to tell you exactly what this is, but it is the thing that's implemented in R or MATLAB if you actually try to do experimental design using the off-the-shelf software. But it's sort of like doing a brute force thing. It actually tries to swap rows until you get a good result. So it is almost like computing the combinatorial solution, actually. So here are the results, and you actually see that the three algorithms that dominate the others, so lower is better, this is error, are the two that we propose, which is the yellow and the black lines, which are sampling and greedy processing on your solution. And then the Fedorov algorithm, which is combinatorial, right? But so we can actually show it takes much longer time, but it does do the best, right? And of course, the gap between these gets better the more ill-conditioned your design matrix is, which is to be expected, right? Because you are able to choose better set of rows in that case. This is just a runtime comparison saying that you actually get orders of magnitude difference between, like, let's say our greedy algorithm and the Fedorov one, which is implemented. So whether you compare in terms of runtime, which is the first quantity, like 1,000 times difference between runtimes, or number of iterations, again, hundreds of order difference. And I'll only show you, we have applied it to several problems, just one real data example because I talked about this road graph thing earlier. So this was trying to predict wind speed, given the wind speed of few locations predicted on the rest. And again, we see that the black and the pink lines, so black is R-greedy and Fedorov, which is the combinatorial solution, actually perform the best. The sampling one seems worse, but it's just that you scale the number of the budget a little bit, and you see it actually just requires slightly larger budget, but then outperforms other algorithms. And Fedorov is, which is the combinatorial solution, is much more expensive. All right. So I guess I don't have too much time, right? Let me just give you a high-level idea of some results for active learning that I don't have time to go into. But again, going back to this idea of, well, so far I told you that you have a design matrix X. It's heterogeneous. If all the rows were similar, then of course experimental design won't buy you anything. But if there's heterogeneity, then it will buy you something, right? We just saw that experimental design can leverage it. Now, what if my X is actually smooth? Maybe it's uniformly sampled, right? But my mapping from X to Y, right, the regression function itself is inhomogeneous. For example, it's piecewise smooth. Turns out in this case, active learning can buy you gains over experimental design, which is actually the same as passive learning. Same kind of story. And this was shown in earlier work where you show you can get better rates doing active compared to passive. And another natural, like this might seem a little constrained. When do you have piecewise smooth functions? A natural setting that comes up is classification. Classification, think of this as one class, and this is another class. This is the decision boundary. Points near the decision boundary are more important than points away from it, and so people have shown results here. And again, the reason you need active is because you don't know the decision boundary a priori or these pieces a priori. So there's unknown heterogeneity. Okay, with that, let me say one other thing. I won't go over this other problem I had about active classification. Yeah, let me just talk about some of the challenges of interactive learning. This is my last slide. There are two sets of challenges I see. One is mathematical. Since these type of methods where the algorithm is interacting with the data are, I mean, they have been around for some time, but the scalability issues and so on are only just now getting addressed. A particular issue that comes up is any kind of statistical grounding, meaning how do you do inference, not just prediction, like guarantees about your inference, model selection, confidence bounds. These are all open questions and very hard questions because there's dependence now between the data points that get chosen. So all of that is a very open direction to look into. Another is more complex types of interactions. Actually, the second project which I wasn't able to get to, we look at feedback. So sometimes the feedback is not just in the form of labels. If you ask experts, it's hard for them to give you a label, but sometimes they can do comparison. They can say this one is more likely to be this value than this value, right? So we have been looking at how you can include like pairwise comparisons along with some direct measurements if you have budget on different types, two types of budget on these two types of labels. And again, the feedback from the users can be very rich. It could be in the form of demonstrations, instructions, relations, and how to exploit all this type of different ways you can interact with the user is an open question. The operational question gets back to what we were saying earlier, which is if you have to do anything like that, interactive data analysis, then you have to work with the experts, right? Because you just don't have the data. You can't take a priori data set and just analyze it. So I think it calls for very close interaction between the domain experts and people doing machine learning, and not just think of those as the domain experts as data sources. So I think that's a key challenge. And with that, I'll end, thanking all the students who have worked on this and really done all the work. Thank you.